Hello students, welcome back. The second problem of this notebook is problem number 30 of section 7.1, and this is not a differential equation problem. It is a proof problem related to analyticity. Prove that the function given as follows is differentiable arbitrarily many times, but not analytic. What do you mean by that? If you have all the derivatives, then the Taylor series applies, so you can expand it as a Taylor series. But in this particular case, the Taylor series is invalid. It exists, but it's invalid because its interval of convergence is 0. So it exists, but it doesn't really tell you anything about the series. By the way, let's begin with a graph of this function. And it looks kind of like this. Let's see. T is less than 0, then function is constantly 0. So we have this part, constantly 0. And then looks like it's exploding. And then later on, it's kind of stabilizing. Not surprised because we get e to the negative infinity power there. So, excuse me, e to the 0 power there, so we have horizontal asymptote there. Anyway, the horizontal asymptote to the right hand side, that's not the key point here. Key point is around t equal to 0, so let's look at this a little bit more closely around x equals to 0. So let's draw this around -1 and +1. Look at this, is it continuous? How about differentiability? Does it look like smoothly joined? How about the slope? It looks very flat, so it looks like slope is 0. And let's see if that is really the case. So let's draw it from -0.5 to 0.5. Yeah, here's the graph. Yes, very, very flat here. So it looks like continuous and slope is 0 and so on. By the way, you can analytically prove that this function is continuous. It's not too bad. Let's see. When t is less than 0, then we have constantly 0, no problem. So limit is 0. How about the right hand side? T is going to 0 from here. Let me expand the font. T is going from 0 here. So this is, let's see, maybe one more step. This can be written as e to the negative of 0 plus. So 1 over 0 is either plus or minus infinity depending upon the sign. This plus sign and this minus. So total we have e to the negative infinity. E to the negative infinity, what is it? That's 0. Okay. That's one way to understand it. And that's more graphical way to understand it. In any case, we have to have a continuous function. So this is a well-defined problem. Now, how about the derivatives? Okay, let's go with derivative computation. And here's the first derivative computation. When t is less than 0, we put the difference of function value over difference of original value, f of t minus f of 0 over t minus 0. And the numerator is just 0 minus 0 because the function value is constantly 0. I don't care what's in the denominator, it's just 0. So far, so good. Right hand side, that's going to be a problem because f of t is going to be this value here. So we are looking at this kind of computation. So this thing is equal to, t minus 0, and then this thing minus 0. And we are looking for this limit computation. And minus 0 drop out. And we get this computation. Now what value is it? How do you calculate it? Well, it is tempting to use L'Hopital's rule, so let's go ahead and do that. Will it help? So let's go ahead and apply L'Hopital's rule. And let's take the derivative of both numerator and denominator. Derivative of denominator is pretty simple. Derivative of denominator is just 1. And let me expand the font even further. I have denominator and exponent, so I'd like to have much bigger font. Okay, this simplified look good. How about the numerator? Exponential remain the same. So by chain rule, we have to multiply the derivative of the inside, right? So negative, and you have negative 1 power, so negative negative plus t to the negative second power. And that's the derivative computation here by chain rule. Let's simplify. What do you get? You get this t squared down there, and then we have the exponential. Let's see, is this something we can calculate? Still complicated, so let's apply L'Hopital's rule once more. Sometimes that helps, right? So let's take the derivative here, 2t, and let's take the derivative of numerator. Exponential always stay the same. And then take the derivative, we have done this before, negative second power. So if you simplify, what do you get? T squared comes down, we have t to the third power, right? And we ended up with this derivative computation. Does it help? Maybe we have to do L'Hopital's rule once more, but stop. Stop and think, and let's look what we accomplished. This was the original, and then you used L'Hopital's rule, and we ended up with t squared down here. Another L'Hopital's rule, we got t cubed. And if you do it again, you're going to get t to the fourth power. And this is counterproductive. You can clearly see this. This is clearly worse than before. So applying L'Hopital's rule over and over again will make it worse and worse. This is not the way to go. So how do you handle this? Well, one way to handle is to do this. One way to handle it is simplifying the fraction. Exponential has this, so let's bring it down there. So we lose this negative, and t goes up here, so we have negative power, and we can apply L'Hopital's rule here, and let's write it as 1 over t. What happens now? Well, derivative of this, negative t to the negative second power. How about this one? Exponential stay the same. And then we have to multiply the derivative of the inside, which is negative t to the negative second power. So what do you have? These two cancel each other out. And then we do not have the power part any longer. We just have an exponential. And what do you get? T is going to 0 plus, so this is e to the positive infinity. So this is 1 over infinity, this 0. That's another way to handle it. This one didn't work very well, but if you flip over and apply L'Hopital's rule, it's a little bit complicated, but you can work out. Still, this is not the method I'm recommending. It works out, and then you can do this all the way through. It's possible, it's just that this is a hard way to do it. Easier this way. Let's see, let's do this computation from here, and then we got that. And then let's take a bit of a break here, and let's apply some change of variable. Let's put x as 1 over t. Therefore, t is 1 over x. And as t goes to 0 plus, x is going to, let's see, 1 over 0 plus, and what is this? That's positive infinity. If you use this change of variable, you can rewrite this one into the following limit computation. Now, instead of t going to 0 plus, x is going to positive infinity, which is down here, and then x is 1 over t, so this is becoming e to the x power, and over here 1 over t is x. This is what we get. And this final expression over here is a benign computation. All you have to do is to apply L'Hopital's rule right away, and then you're going to get one over e to the x, and then that's 0, isn't it? 1 over infinity, so we have 0. So it's about the same as this computation, because L'Hopital's rule computation was easier, but we had to take this change of variable, which kind of corresponds to this chain rule computation and this kind of manipulation. It's a kind of push. But the second method is going to be a lot easier. I mean, second method will turn out to be a lot better if you go over to higher derivative computation. Let's erase all these. We don't really need it, because if you just open it up, we have everything already. Using the L'Hopital's rule method, just straight ahead L'Hopital's rule using the power rule, and then change of variable method, they're all here. And in the end, the conclusion, left-hand side limit is 0, right-hand side limit is also 0, so the limit exists, and the common value is the limit, and that is the derivative. Same as what we expected. Let's look at the graph again, and the graph was very, very flat. Around here, yes, slope is clearly 0, isn't it? Now let's work out the same thing for higher derivative. Let's go to the second derivative computation. Similar kind of computation, f prime of t minus f prime of 0 over t over 0, like this. And then left-hand side, what you have? We have constantly 0, so left-hand side, everything is 0. The derivative, second derivative, everything is 0. So numerator is 0 minus 0. And denominator, it doesn't matter. The total fraction has to be 0. So left-hand side is easy. Always we have 0. To the right-hand side, we need a problem, because f prime of t, you have to calculate it according to the chain rule. And what you have, exponential times by chain rule, we have t to the negative second power, and we have to calculate this limit. How do we do that? As I told you, my suggestion is to use the change of variable. Yes, you can work out with L'Hopital's rule directly, but that's not what I suggest. This computation, or let me write like this. Okay, and then I don't need minus 0 anymore. And then flip it down, and then we get 1 over t. I hope that's right, isn't it? We multiply t and then, oh no, excuse me, it's t squared, t. Let's negative second power, bring it down. Oh, you have to, let's see, is this what we get? Negative second power, okay, bring it down. Okay, alright, this is a derivative computation, okay, alright. Okay, alright. Okay, and then we use the change of variable, you see. And bring it up here, and we have 1 over t cubed. And this one, e to the 1 over t. We don't have this negative sign anymore. And then we use the same change of variable. Instead of t, let's change x is going to positive infinity. And then this is e to the x power. Oh, what did I do? Sorry about that. Okay, e to the x power. And then this is x to the third power. And let us put the remainder here. X is 1 over t, therefore t t is 1 over x. T is going to 0 plus. X is going to 1 over 0 plus, which is positive infinity. And that's in action here. And how do you calculate this limit? This is a benign limit computation. Just apply L'Hopital's rule 3 times, and the numerator will disappear. Denominator will stay as exponential, and that's 0. So what did you get? Right-hand side limit is also 0, so the conclusion is second derivative is also 0. Let me erase this. I don't really need it because everything is already hidden here. Change of variable is more useful, the same thing I just told you before, and consequently we have this conclusion. Second derivative is also 0. Now, how does it help us calculating the general derivative computation? Just apply the same kind of argument. You see, if you take the derivative arbitrary many times, what do you get? Exponential always stay the same, and then timed by chain rule, you have to multiply some power function of t, power function of 1 over t, to be a little bit more precise. And then by product rule, we have all those things added up there, but you can always factor out the exponential part. That doesn't go anywhere because of this chain rule. In general, what you get, this derivative part is, as a matter of fact, a polynomial of 1 over t. It's complicated polynomial, but I don't care. It's a polynomial anyway. It has finite degree, and exponential does not go anywhere by chain rule and product rule, so it stays. You can factor out. In the end, what do you get? Exponential, we bring it down, and you have a polynomial of 1 over t, or polynomial of x over e to the x after change of variable. What did you end up with? Another benign limit computation. Just apply L'Hopital's rule 5,000 times, or whatever. The numerator will become 0 anyway. It's a polynomial. Polynomial degree of 5,000. Then after 5,000 derivative computation, it's going to go down to 0. Exponential will stay all the way the same. So we have to have 0 in the end. So what do you have? Nth derivative is also 0. Left-hand side always 0. Right-hand side is 0 due to this L'Hopital's rule and change of variable. Finally, the conclusion. The Taylor series computation becomes like this. The derivatives are all 0, so coefficient is all 0, so you get only 0. And then, of course, that's not valid at all. Look at the graph. This is not a constant function. Yeah, to the left is constant, but to the right is not a constant, which means this Taylor series expansion is invalid. Radius of convergence is actually 0, and interval of convergence is 0, as a matter of fact. So here's an example of a continuous function which is differentiable infinitely many times, yet not analytic.